So can you see this?
Yes.
Yes. All right. So, okay. So without going further for a delay, so I'm just going to go and talk about viscosity. Okay. So I believe you learned viscosity from Dr. Yana before, and then I've touched into the viscosity study last time, a bit on that. Now for today, we are going to learn about the idea of viscosity. And remember, when we talk about viscosity, it is based on the internal resistance. Oh, sorry. Within the fluid. Okay. And this is towards the fluidity or fluid flow. Okay, just a reminder how the internal resistance work. It means in the molecular level, you have a condition where it okay, so in the molecular level, it means that you have a condition where you have your water, okay, for example, like this one, flows from side to side, okay. So it has some internal resistance inside this water. However, because the internal resistance is low, so the viscosity is considered to be slow and the water can move freely from side to side like this. Again, if I'm using my hand sanitizer, the movement is not as fluid as the water just now. So it means over here, we will have a different viscosity. So this is more viscous. So the fluidity is much better. So because of that, this should be more viscous than water. Okay. So how do we know what is the viscosity of this and this one? Okay. So before this, we have researchers from all around the world studying this part of the study, which is on viscosity. And we already know the numbers for this viscosity, okay? And all the numbers are stated inside the textbook or inside any other fluid mechanics book that we are going to use, okay? So this number is used worldwide, okay? And we don't have to do any other experiment to check on this number again because I believe the experiment was done properly before and everyone else is using the same number. It means for water, it has a certain viscosity number, and also for whatever liquid that we have their viscosity number. Okay, so what are we trying to do for today is we are trying to learn about the fundamental ways of getting this number. So how the researchers from years back did their experiment and how did they get the number for mu. Okay, so how did they get the number for that? So the experiment is based on this experiment, which is we have two plates sandwiching a liquid in the middle like this, two plates. Okay, so one of the plate is moving and another plate is fixed. Okay, so what happened over here is, all right, so how they did the experiment, in between these two plates over here, same surface area and everything, they fill in the plates with fluid in between. Okay, and because the study is more towards liquid, we can say in between here we have liquid. Okay, and the liquid has a thickness of L. Okay, and then here I put some definition. L is the thickness. Okay, so the plate over here, this part which is moving, has a surface area. Okay, and we denote it as AS, which is area of surface or surface area. Okay, so the experiment is done by putting liquid in between two plates, sandwich it together. Okay, this is like an action when you did your biology lab or science lab, where you try and take water from the drain and put it on top of a plate, okay, or a glass, and then you put another glass on top of the water from the drain. For example, You clamp it together or you sandwich it together and then you put it under a microscope. Okay, I think have you done that?
No.
Tak pernah Tak pernah ada eksperimen ambil air dari longkang, letak atas plate kecil and then letak air setitik, letak satu lagi plate dan letak bawah mikroskop. Tak pernah buat
Pernah sir.
Pernah kan? Okay, saya rasa pernah buat kot. Sains pernah buat. Okay, so it's the same idea like this, but instead of you are going into the microscope, what we do is we pull one of the plate to one side. For example, I'm going to the right side like this, and we want to know how much force is required. Okay, because this is moving this way, so it's shear force. Okay, or how much stress is required to pull this plate out to the right. Okay, if the liquid has a low viscosity number, it will be much easier to pull, so the force will be lower. If the liquid has a very, very high viscosity number, it will be a hard task for us to pull it, and it needs required a higher force to pull it to the right. Okay, so that's the idea of the study for viscosity. We have a liquid, we pull it to the right at a certain force, and then we know the force. Now from there, we can know the viscosity. So Fs is shear force. Our S over here is shear stress. Okay, what's the connection between this? Shear stress is equal to shear force divided by the surface area, or the shear force is equal to shear stress multiplied by surface area. Okay, the unit for shear stress is the same as the unit for pressure, which is Pascal. Force has a unit of Newton. Okay, all right, so we have force of shear, okay, and then shear stress, and we want to know what is the velocity of the plate, so that when the plate is moving, we know what is the velocity. So V should be equal to plate velocity. Okay, all right, so the next part is this part where we want to define a few things. Number one, here we use U over here and U over here. Okay, what is U? U is the liquid velocity. Okay, so liquid velocity means over here, we want to know what is the liquid velocity and what is the liquid velocity over here. Okay, so why is it important? Because if you have a fixed plate like this, the U over here at the fixed plate, for example, down here, we put it as number 1. This is point number 2. Okay, so U1 over here should equal to 0 because the fluid is sticking to the plate that we have at the bottom and the plate does not move. So it will become 0. However, if you have a liquid that is sticking to this plate over here, because the plate is moving to the right with a velocity of V, the U at this particular plate, or when it sticks to this plate, U2 should equal to V. Okay, so it means from here 0, here you'll have V. So what happened? So the U will keep on increasing from bottom to the top, okay, because the top part is moving and the bottom part is fixed. So the velocity of the fluid moving to the right is based on the location of the study, okay. So how do you find out what is the location of the study? So we will use the definition of Y. Here is Y1, here is Y2, okay. So Y, it means that Y is actually the vertical location. Meaning, this is point 2, so this is Y2, this is point 1, so this is Y1. So, point 1, Y1, point 2, y2. Okay, so any point in between 1 and 2, you can denote it as any point over here, yx for example. So yx is a location where it is in the middle, for example. Okay, so any location is denoted by y over here. So u is liquid velocity, y is vertical location, v is plate velocity. So these two are not the same. Plate velocity only involve the plate. U liquid velocity involve all the liquid here. Okay. A good example to understand the liquid velocity is, for example, if I have somebody over here holding to a pole, for example, something that is not moving. Okay. Okay. He or she shares a string or a rope together like this. Okay. With three of her friends or his friends. Okay, like this and like this. Okay. Nothing happens if you do it this way. So each one of them is holding a rope, for example. Okay. And this person at the end is holding a pole. So this is a fixed pole, for example. Okay. So what will happen if this person is moving to the right at a certain velocity? So what happened? This person will move to the right. And because they are holding the same rope, so this rope will pull the second person to the right also, but not with the same velocity because this person is pulling it. So this person must be faster than this person, okay? And because of this, we have connection with the third person over here, okay? And lastly, this person will still stay at the end because this is a fixed pole. So what happened? The one near to the fixed pole will stay at the fixed pole. The one near to this person, okay, will be slower because left side is holding the rope for the fixed pole person, and the right side is holding the hand for the one going to the right, okay? And the fastest person will be on the top, okay? So this particular condition is the same over here also. One is fixed, the other is moving. So the velocity of liquid inside here moving to the right will be also moving faster from bottom to the top. Okay. It should be the same if it's the other way around, meaning if this is fixed, this is moving, so the velocity will be this way. Okay. Any problem understanding this?
No, sir.
Oh,
No, sir.
okay. I think it should be a simple idea here. And what happened here is this liquid is having a condition called as deformation. Right? Because the liquid is moving based on the shear force and shear stress over here. Okay, why is it important for us to know this? Because the equation that we are using to understand the viscosity from this study is based on this equation over here. First, shear force is equal to shear stress multiplied by area of surface. Okay, so what is shear stress? Shear stress is equal to mu, which is dynamic viscosity, du dy. Okay, so what is mu? I put it here. Mu is dynamic viscosity. When you heard the word dynamic, it means the movement or moving. It means this is the viscosity that happens during the movement of liquid. So we call it dynamic viscosity. Okay. So you have mu du dy over here. So this is the equation. So if I put this here, Fs will be mu du dy multiplied by A. All right, what is du dy? Okay, du dy, if you learn it from mathematics, it means u2 minus u1 over y2 minus y1. Okay, so where is u2? So u2 over here is equal to v, u1 is equal to 0. So it becomes v minus 0. Okay, Some of you will ask me which one is 1, which one is 2. Usually the fixed one, I'll put it as 1. The moving part, I'll do it as 2. Okay. So U2 minus U1 will be V minus 0. How about Y2 minus Y1? So Y2 minus Y1 will be the whole length from bottom to the top, and then it is the same as the L that we have over here. So Y2 minus Y1 is equal to L. Alright? So du dy is equal to V over L. This is not something coming from somewhere else, okay? It is based on this picture here, U2 minus U1, so V minus 0, okay? Y2 minus Y1 will be this thickness over here, L, all right? So we can rearrange the equation on top so that the equation will be, so this is the one that you need to remember, F shear is equal to tau shear, shear stress multiplied by surface area is equal to mu du dy A, and it is equal to mu V over L A. Alright? So you get the idea for Fs. Number 2, shear stress is equal to mu du dy, and it is actually equal to mu V over L. Alright, and remember the unit for this is Newton. The unit for this is Pascal. Okay, and the third one is, what is the kinematic viscosity? Kinematic viscosity is the viscosity when the number of viscosity will be, dynamic viscosity will be divided to the density. So kinematic viscosity is this one. It is equal to mu divided by rho, which is dynamic viscosity divided by rho. Okay, and the unit should be equal to meter square per second. Okay, so the unit for mu, okay, is equal to par dot s. Okay, so this is the unit for mu. Alright, it might be par dot s, or it can also be Newton second per meter square. Okay, so it will be a lot of numbers over there or unit, but usually I will use par dot s over here. So meaning Pascal second, okay, or it can be Newton second per meter square. All right, any question on this? Let me log this way. Okay, any question?
No, sir. No.
No. All right. So that will be it for the calculation or equation. Now, I will show you some variant of calculation that may happen in the study. Okay, number 1 will be this variant, which is the one that we did just now, which is we have 2 plates. Okay, one is moving. It doesn't matter the one on the top or at the bottom. Okay, and this one is fixed. Right, so it's moving this way. So for this one, what we will have is we have shear force, shear stress, and also velocity. All right, so this will be the thickness. Okay, and this will be mu inside here. All right, so to find out mu, we can use F shear equals to mu V over L multiplied by A, or we can use mu du dy A. Okay, all right, so how about or it is actually equal to shear stress times A. Surface. Okay, And this one is just mu V over L or equals to mu du over dy. All right, this is the first condition. Okay, so in case you want to find out what is mu, mu should be equal to either Fs multiplied by L divided by V multiplied by As. So what I did here was pulling everything out from the right side because we want it to be in terms of mu. Or if you are using this equation, mu should be equal to shear stress times L over V. Okay. All right, so it's either one. It depends on whether the question gives you the area or not. If the question gives you the area, you can find it through force. If the question did not give you the area and provides you with everything else, you can use this equation. It's one or the other. Okay. So next will be on the second type. The second type is sometimes they want to study about the viscosity between two fluid. So we have top plate on the top like this, and then we have another plate at the bottom like this. Instead of one moving and one fixed, both of them right now are fixed. All right, so what happened here? We have another thin plate. Okay. Okay, and it is moving to the right with a certain force of shear, shear stress, and also certain velocity. Okay, what happened here? You might have two different liquid, so two different dynamic viscosity. We have this as L1, for example, and this is L2. Two thickness, two different liquid, one thin plate moving to the right. So what will happen here? We need to rearrange the equation differently. So to find out what is the shear force, it is equal to force of shear at the top plus force of shear at the bottom. Meaning, we are separating the calculation for the top and at the bottom over here. So how do we do that? Simple. We take mu. V should be the same because the plate that is moving is on the middle. So both of them are receiving force from this plate. So same V, mu 1, for example, to the top, over L1 multiplied by A. Okay, so A should be the area of surface here, and it should be the same for 1 and 2. So for this question, for thin plate, A1 should be equal to A2. All right, so don't worry. So the A for the plate should be the same. So that's why I do not put any 1 or 2 over here because it's the same. Okay, so plus at the bottom, you will have mu2 V over L2. Okay, and then A also because it's the same thing. All right, so at this moment, what you will see is V should be the same, A should be the same. So because the V is the same, so you will have constant V. Why is it constant? Because this plate is the one moving. All right, if this plate is moving, this plate is moving, I will not be constant. All right, but right now, these two plates, one is fixed, one is moving. So this will be a constant. All right, so what can I do here? So you can get your shear stress, shear force like this. Or if you go for shear stress, it will become mu1 and only V over plus mu2 V over L2. So the difference is we don't have dA over here because force is shear stress times A. Shear stress does not have any area. Okay, so that's the second one. The third one is different. Okay, so from what you can see here, the fluid is non-moving. you have a moving plate. Then when you move the plate, the fluid is moving. Despite both of them are fixed plate, one of the plate in the middle moving, so the liquid will move according to this. Okay, so what will happen? The velocity will be like this. Okay, the velocity of liquid. Same also. All right, so the velocity of liquid over here is 0. Here will be 0. Here will be the velocity of the plate. Should be the same as the velocity of liquid. All right. Next, the third one is, this is a condition which is different, which is it's either we have a flat plate like this, fixed, and fluid is moving on top of it, for example. Or we have a plate like this, which has fixed plate, for example, like this. Or we might say this is a pipe, okay, a cross section of a pipe. And instead of these two moving, the water inside is moving. Okay. Why is it having this curvature over here? Because like I said just now, liquid near to the plate will be slower, will liquid further out from the plate will be much faster. So here we have a fixed plate, so here is slower velocity, slower and faster here. Okay, so what will happen here? Okay, sometimes when this question appears, they will give you an equation that looks like this. I'm just putting out some equation here. It's not, might be true, but might not be true, but we're just going to use as an example. For example, like this. Okay. So what happened here? Instead of these two is moving, now the plate is not moving. So over here, we don't have any V, no velocity of plate. All right. We don't have any force from plate also. So what happened here? So the study will change into, for example, shear stress is equal to mu du dy. We cannot use V over L because there is no V, and the thickness over here is not important. Important actually, depending on the situation. But at this point, we only have L, we don't have V, so we have two unknowns. We don't know mu, we don't know what is V over here. So what we need to do is, this Uy over here needs to be changed into du dy. How? I think you have to differentiate. This is calculus all over. So what will happen here? Uy is 3 over 4 y squared plus 4 over 5 y. So if you differentiate into du dy, it is supposed to be 2 times 3, 6. 6 over 4 is 3 over 2y plus 4 over 5. Is it correct? Anyone can confirm this? Yes. Is it? This is like 12 years ago for me. 2 times 3 is 6. 6 over 4 is 3 over 2. This is 1 times 4 is 4 over 5. And y is gone over here. 2 over here becomes y. All right, so now your shear stress for a certain y in the study will be equal to mu 3 over 2y plus 4 over 5. Okay, so if I talk about shear force for a certain y in the study, so it becomes mu 3 over 2y plus 4 over 5 multiplied by area. Okay, so over here, we cannot use the V over L condition because it involves moving fluid and fixed plate. Okay, so these three conditions will be different, and you will see these three conditions when you are doing the examples, or when you are dealing with assignments and tests. All right, so make sure you understand these three, so that you need to remember the difference is here you only have two plates, so we don't have top and bottom. Here we have a middle plate over here, thin plate. So you have a top part and a bottom part. Lastly, we don't have any plate moving, but we have equation for the fluid movement. So this will be the equation. So the y itself depends. If the y is here, 0, so y over here is 0. Maybe if the y is here in the middle, 0.1 for example, so you put in 0.1 in the question. All right, so before we go further, any question on that? Because after this, I'll show you an example for both of the condition.
So yang nombor 3 ni dia punya velocity tu macam fleksibel ke macam mana sir? Ke beza-beza?
Flexible. Oh, the velocity over here, this one.
Yes.
Okay, for this one, we don't have the velocity, but instead, kita pakai velocity of liquid here, and the number will be different in terms of y. If, for example, here the y is 0, this is y equals to 1, for example, and then the question asks us to find out what is y when what is the shear stress when y is 0, or when y is at the plate. Okay, so if y is at the plate, it should be 0 lah. All right, so I put 0 here, so the y over here will be 0, so it's just mu times 4 over 5, for example.
Okay.
Okay, but if it says, the question says that, okay, the y is equal to 1, then I change the y over here into 1, so this part over here should also be 1. So the mu will be multiplied by 3 over 2 times 1 plus 4 over 5. So it depends on the question.
Okay, thank you, sir.
Okay, and sometimes the question will give you the numbers here, 1 and 0, but they will not use the wording 1. They said, okay, what is the shear stress at the middle of the pipe, okay, at the center of the pipe. So the center should be here, so you should locate, and it is 1, for example, and use this number. What is the shear stress when the location is near to the plate? So this is the plate, so it should be 0. So you can just use 0 for the number.
Okay, thank you, sir.
Okay, sure, welcome. All right, so I believe that will be the idea of viscosity and also this part. Okay, so this is an example. So I'm going to do these two examples for you guys, and I will find out any other examples for you to do for tutorials. All right. Okay, so this is question number 1, viscosity. Two parallel and stationary flat surfaces separated by a 4 cm gap. If I see something that is not in SI unit, I will change it. So 0.04 meter. Having a viscosity of 0.834 Newton second per meter square. So this is because this is Newton second per meter square. If you check from the top, it is dynamic viscosity. If it is meter square per second, it is kinematic viscosity. Right? So right now we have the question to be, so this will become the kinematic viscosity, All right. Assuming the flow velocity varies linearly, determine the force required to move a thin plate when the plate is at the midplane between the surfaces. The plate area, so this area over here, is 1 meter square and move with a velocity of 5 meter per second. So V is 5 meter per second. And the area of surface over here is 1 meter square. So many will ask me, which one is the area of surface? Area of surface is the surface that is moving. Okay. Now H1 is 2 cm, so 0.02 meter. This is also 0.02 meter. Since there is no definition whether the top part and the bottom part is different, so it means here the mu should be the same because there's no definition whether this is mu1 or mu2. So we consider both of them are the same. Okay. So the question asks, what is the force required? So the force required, okay, so that is shear force. So to do the calculation, first we need to do the equation correctly. So force of shear is equal to force of shear at the top plus force of shear at the bottom. Okay, so it is equal to mu A V over L. Okay, so V is the same, L1, A is the same, mu is the same. So for this question, mu1 is the same as mu2. Okay, so I don't put any numbers here, so you get the idea. And then mu A V over L2. So let me put 1 and 2 here. Okay, so that I will not generalize it that way. So M1 is equal to M2, same fluid. If it's a different fluid, mu1 and mu2 should be different. Okay, so it is equal to mu. Okay, so mu A should be the same, V should be the same, L1 and L2 are the different part of this study. So to find out what is force of shear, you can either put the numbers in right now, or you can do like a factorization. So mu A V, for example, and then 1 over L1 plus 1 over L2. So mu should be here 0.834. Area should be 1 meter square. V should be 5 meter per second. And then here is 1 over the thickness 1, 0.02 plus 1 over 0.02. So the shear force should be equal to 0.8234 times 5 times 1 over 0.02 plus 1 over 0.02. So the answer should be 417 Newton. Alright, so this should be the same as this one. Okay, so we're done. Any problem with this one? I think this is a very fundamental question so that we get an idea on how to do the calculation. Any problem?
So far so good, sir.
So far, so good.
No,
All
sir.
right. Next one will be the next viscosity question. Okay. The space between two square flat parallel. Let me change it first. The space between two square flat parallel plates is filled with oil. Okay. So this is specific weight. All right. So remember, specific weight is rho times G. Okay, why does it give you the specific weight? Because they want us to extract the density from here. Okay, and it can be in this unit or Newton per meter cube, the same thing. All right, so the area for each of the plate is 2,500 cm square. Okay, so we have different units over here. 2,500 cm square is equal to 0.5, 0.25 meters square. Okay, the thickness of the film is 15.5 millimeter. All right, 15.5 millimeter divided by 1,000. So zero point zero one five five. So 0.0155 meter. The velocity distribution flow is given by, so U over here. So this should be Uy. So this is the Uy, in which U is the velocity in meter per second at a distance y meter above the plate. Okay. So this question does not have any pictures, but you can get the idea. The picture should be somewhat like this or like this. Okay. All right, but it says over here 2 square flat parallel, meaning 2 square flat parallel like this. So meaning the liquid is moving in between two plates. All right, so in which U is velocity? So take the kinematic viscosity of fluid viscosity as 5.6 times 10 to the power of negative 4. So what we have here is, since it says kinematic viscosity, it is equal to kinematic viscosity. And to find out the dynamic viscosity, it is through this equation here, mu divided by density. Okay. So determine the shear stress and shear force subjected at y equals to 0 and y equals to 15.5. So this will be the question. The thickness is 15.5, so y equals 15.5. All right. Okay, so what do we do over here? So what do we do over here right now is we take this equation here and change it in terms of du dy. So that's the first thing to do. So uy is equal to 4y squared over 5 plus 3y over 4. Okay, so if I change it into du dy, it should equal to 2 times 4, 8. So 8 over 5y plus 3 over 4. Okay, so now you should be able to use it in the calculation. Okay, number 2, they give you the kinematic viscosity. So we need to find out what is the mu. Okay, so to find it out, first we have to use the rho g calculation here. So okay, to find out what is the density, it should be okay, the weight, specific weight divided by gravitational acceleration. So 9450 divided by 9.81. So the density will equal to 963.3 kilogram per meter cube. Alright, so when you get that, this number, then we can do the calculation for this one. So kinematic viscosity is equal to dynamic viscosity divided by the density. So to find out the density is equal to mu divided by, we are not finding out the density. We are trying to find out the mu, okay? So to find out the mu is equal to density times kinematic viscosity. So it is equal to 963.3 multiplied by the velocity, which is, is it given here? Oh, sorry, this is not this is not velocity. I'm sorry. This should be the kinematic viscosity. So 5.6 times 10 to the power of negative 4. Okay, so this is kinematic viscosity. Sorry. So it should be 963.3 times 5.6 e negative 4. So mu should be equal to 0.5394 Pascal second. All right. So when this is done, and this is done. So now we can do the calculation to find out shear stress and shear force. Okay, how do we find out shear stress? Okay, we use the equation. Okay, and we use the number 0 here and 15.5. So the equation first, shear stress is equal to mu du dy. Okay, so it is equal to mu 8 over 5y plus 3 over 4. Okay, so if the shear stress for 0, it should be equal to mu, or we can change mu into numbers right now. Zero 0.5394 multiplied by 8 over 5 times 0 plus 3 over 4. Okay, so this cancels out, so it becomes equal to 0.5394 times 3 over 4. 0.4046 Pascal. So this answers the first part. What is the shear stress when this is 15.5 millimeter, which is 0.0155? So it is equal to 0.5394 multiplied by 8 over 5 times 0.0155 plus 3 over 4. So the answer should be okay, so 8 over 5 times 0.0155 plus 3 over 4 times 0.5394. So the answer over here should be 0.418. Okay, Pascal. All right, so we have this and we have this. So to find out what is the shear force is just equal to tau shear times area. So shear force for 0 when y is 0 is equal to 0.418 times the area, sorry, 0.4046. I picked the wrong number. So 0.4046 here, okay, multiply by the area, which is given here as 0.25. So it is equal to 0.1012 Newton. Okay. And then if the shear force is at y equals to 0.0155, it's equal to the shear stress at 0.0155 multiplied by the area, so equals to 0.418 multiplied by 0.25. Zero 0.1045 Newton. So this will be the answer for all the questions given to you, which is shear stress and shear force at y equals to 0 and y equals to 15.5. Okay. So that will be the answer for the question. So this is the first part, shear stress. Second part, shear stress over here. Third part, and the fourth one.